Good morning, good afternoon, and good evening for all the audience. So my name is Ahmed Gomaa. I'm a stimulation fluid expert. I've been working in stimulation fluid for around 15 years now. Currently, I'm intervention chemist fluid specialist working at BB. I joined BB 2017, so for almost right now 7 years. Before that, I was working with the Baker Hughes pressure pumping. I've been there for 6 years. And before that, I did my PhD, which is also with stimulation fluid. So I graduated 2011 from Texas A&M, and my PhD topic was at stimulation, especially in the diversion part. So I have around 17 patents and 13 journal paper and around 73 conference papers. So majority of them was related to acid and hydraulic fracturing. So just like this is a quick intro about myself. For today's topic, we will be focusing on as an introduction for acid stimulation. So what we will learn, what acid stimulation is and what type of acid we are using and what's a typical treatment for acid stimulation. So just let us start. So let's start with a quick definition. What does acid stimulation mean? So acid stimulation is actually unsteady flow, is non-isothermal. So it's actually create heat as acid reacts. It's a 3D flow, especially for coming out from the perforation. So the flow will not be linear or purely radial. It will be like actually 3D. And the flow initially will flow happening in the porous media with chemical reaction. So we're talking about acid, which is a chemical component. That will actually do two things. It reacts with the surface of the rock and dissolving the surface of the rock. As you are dissolving a part of the rock, definitely what's happened, the porosity and permeability change. If you are dissolving, it leads to porosity increase and reflecting the permeability will be increased. However, we're talking about reaction. And if you have a reaction, you have a reaction product, which majority of it or some of it can be soluble in water and some of it cannot be soluble in water. And the part that is not soluble in water will be precipitate, which will do the opposite, will reduce the porosity and reduce the permeability. So hopefully by the end of acid treatment, the amount that we dissolve will be much higher than the amount that we precipitate, ending with a higher increase in the porosity and permeability. And in general, when we're talking about acid stimulation, we're talking about three main aims. First, increasing, okay, me have my pen, increasing well productivity, improve the oil production, having a higher oil and gas rate at the similar drawdown pressure. The second, if we have a scale, and our idea is dissolving all the scales that can happening in the wellbore or can happening in the fracture that's connected to the reservoir. And mathematically, we are looking to reduce the skin factor, the S factor from the Darcy flow. As you are reducing the skin factor, you will be able to get a higher productivity and removing it, especially from near wellbore area. So this is like a quick and simple definition of acid stimulation. The key question that as a petroleum engineer or as a completion engineer or as an intervention engineer, you need to answer it when I need to use an acid. And based on my experience, I found only one answer that can allow us to use an acid for a wellbore. And the answer is when you have damage. We typically use acid when we are seeing damage in the wellbore. We don't use acid just for increased production without knowing what's happening downhole. Acid is all the time connected to some sort of damage that I need to remove. And by removing this damage, I will be able to restore the permeability or to slightly increase the permeability, getting a better reduction, a better improvement in oil and gas production compared to the damaged well before the treatment. And the definition of damage is pretty simple. It is something unusual or unexpected reduction in oil and gas production. So as producing from the wellbore, usually your reservoir pressure will go down, usually your rate will go down. That's not a damage. That's like a performance of the reservoir parameter or reservoir expected reservoir reduction in pressure. What we are talking here about damage, something you are not expecting to happen, something unusual to happen. And this one can be taken a different form. It can be really gradual, really slow reduction, really slow, like gradual reduction, and that's something like that will be scale. Scale take a little bit time to build up and to have the effect on the production. So usually you will see scale forming or scale deposition taking slower time, especially if inside the wellbore. And as a result of it, you will see a gradual reduction in the oil and gas production. It may be happening really rapid, very, very quick and very happen. So suddenly you see the production is going down. And you can see it always the case in the three, oil and gas and water. And that can be happened if you are plugging something. If there is fines that being generated, if there is something that block the perforation, so it's something that can be happened and immediately. Or you can see it if you are actually monitoring two parameters, the gas oil ratio and the water cut. Gas oil ratio is a good indication that you are having additional pressure drop that's happening inside the wellbore, which lead to more gas leaving your oil and your gas oil ratio increase. So that's kind of a good evidence that you're having additional damage that you are looking for. And water is something that we don't like. We don't like to produce water. We are drilling the well for the oil and gas. So water is a component that we really like to keep it under downhole. So for increasing the water cut, that's something that is a part of damage that we need to reduce it either by shutting it off or by enhancing the oil zones more to produce more oil coming from it. So we have multiple sources of damage, and the damage source will be depending on which case we're having. If it's a new well, usually the damage will coming either during the drilling phase or the completion phase. Drilling can be from the mud definitely, or from the cementing. It can be a mud solids, mud filtrate, and the same for cement solid or cement filtrate. Or during the completion when you are doing the perforation, maybe you have some sort of compaction happening to the perforation, you have a lot of debris in the perforation that you need to clean up. So if it's a new well, you will always like to review the drilling program, the completion program, and pretty sure nothing will be happening there. And that will be the key to identify what type of damage you are having there. If the well is not new, it's like a 2 years, 5 years, maybe 10 years old well, in this case, the type of damage they're expecting there will be mainly two types. Either the scale, like an organic scale, like calcium carbonate, calcium sulfate, iron sulfate. So some inorganic that precipitate because of there's maybe change in pressure leading to change in water chemistry, allowing more mineral to be precipitate with time, can be inorganic, or can be actually organic, can be asphaltene or paraffin. Asphaltene by pressure, by reducing the reservoir pressure, also the heavier component concentration go up and start to precipitate. Or you're having some sort of a cooling effect or some sort of a temperature change that allow paraffin to deposit downhole. So that can be anorganic. So that can be happening for the old wells, or something related to clay issue or emulsion issue. You have some sort of a EOR program or water injection program that allow us to have a clay swelling or an emulsion that happened for the older producing well. The last category, if you have an injection well, and injection well usually will be related to the injection procedure that you have. You have actually injecting water that will have a water chemistry different than the downhole water, which when you mix two water, expecting all the time to have some sort of a scale. Or you have surface water that has a lot of bacteria, and you are right now introducing a harmful bacteria in your reservoir that can do a lot of damage. So for injection water, you need to check the water chemistry that you are injecting and how it's compatible with downhole, and also be sure that you kill all the bacteria before injecting the water. You don't want to put a new bacteria downhole because it can cause a lot of things, especially H2S and acid corrosion bacteria. So that's two really harmful one. Also, the water that you're injecting, is it solid free or has some fines that can actually plug your formation? That's your like filtrate some solid that can go and precipitate inside the pores, reduce the permeability. And the last one is how it's compatible with a downhole clays. Clay is very sensitive to the water. So if you are injecting water, you need to be sure the water salinity that you are injecting or adding some sort of a clay inhibitor that will minimize the clay or any bad negative effect from clay. And similar to it, emulsion. You'd like to be sure the water that you're injecting does not have any surfactant or any active ingredient that can actually stabilize the emulsion with the oil, because the viscosity of it will be much higher and the production will be lower because of the higher viscosity of the emulsion product. So that is simply the source of the damages that you can expect, depend on which case you are, for new well, old well, or injection well. And when you identify each one, that's when the acid treatment become needed for the treatment. So we mainly have a two type of acid stimulation treatment. The first one, we call it matrix acidizing. The second one, we call it fracturing acidizing. And the distinguish between these two is really simple. It is actually depending on the rate and the pressure that you, as a completion engineer, decided to use during the treatment. If you said, I'm doing matrix acidizing, this means the injection rate that you use, that you will apply to the surface, and the injection pressure that you apply to the surface will be less than the fracture pressure of the formation. So, for example, if the formation breaks down at 8,000 psi, so you will keep your rate and pressure less than 8,000 psi, maybe 7,000 psi, maybe 6,000 psi, some gaps there. So to be sure that all the acid that you are injecting, actually, it will flow inside the porous media and will not create additional fracture. But if there's some fracture downhole, it can go through it as well. But it will not create additional fracture because the injection rate and the injection pressure is actually less than the fracture creating pressure. And for matrix acidizing, we have two main types depending on the formation that we are injecting in. The first one will be sandstone acidizing, and that's represent when you are injecting acid in sandstone formation. And usually, if we're talking about sandstone acidizing, that we'll discuss later, we're talking about HF acids, some sort of hydrofluoric acid treatment. The other type of matrix treatment is called carbonate acidizing, and as from the name. In this case, we are injecting the acid in carbonate formation. And in this case, we mainly use HCl or some sort of organic acid. But that's a main two definitions. So matrix acidizing, simply pressure rate less than frac pressure, and two types. Sandstone acidizing for sandstone formation, carbonate acidizing for carbonated formation. On the other hand, there is something called the fracture acidizing, and again, from the name, in this case, you can expect the pressure that you are used, the injection rate that you are applying will be higher than the fracture pressure. And in this case, if your fracture pressure is 8,000 psi, so your rate and the injection pressure will be higher, maybe 8,500, 9,000 psi, much higher, to be able to create the frac and inject the acid actually in the frac that you are creating. And that's what we'll do right now. It will etching the surface of the core, the surface of the frac, and creating a gap. So when this frac is closed again, there will be a gap with higher conductivity, and that's how it creates the conductivity. And usually fracture acidizing is mainly for carbonate formation, not for sandstone. So when you hear fracture acidizing, that's mainly carbonate formation, because carbonate formation, you can dissolve significant amount of it and create this etching fracturing that will have a good production. So maybe that's one more thing is how do you select between acid versus fracture treatment? And that's a main key point that as a petroleum engineer or as a completion engineer, you like to distinguish. So when you are using acid fracture, when you are using acid or matrix acidizing. So that will be depending on the type of the formation that we are dealing with. So the first case, if you are talking about I have no damage and my permeability, which K by H, the permeability by the thickness of the formation is very low. As the keyword here is actually the no damage. So if you see that you have no damage, in this case, definitely matrix acidizing is not applicable something. And you should not use acidizing. As you don't have damage, acidizing as a matrix acidizing is not applicable for it. The only part that's good for this case will be the hydraulic frac. And depending on the formation, if you are talking about sandstone formation, that will be probed frac. If you are talking about carbonate formation, in this case, probed frac can be a good one, or maybe acid frac can be a good one. But for no damage, we are talking about matrix acidizing is no go at all. No damage, no acidizing for matrix. If you are talking about there is some existing damage, and this damage actually be in the near wellbore area, and the permeability of the formation is good, in this case, that is the ideal case for matrix acidizing or for matrix damage removal. That is the case that we are running the acid part. So that's the part that is the key word that we are having. If you are seeing there is a damage, definitely your mind go directly to matrix acidizing or acid treatment for your matrix to remove or bypass the damage. And these two words will be depend on type of the formation that you have. So when we are talking about removal damage by acid, usually that's a good for sandstone formation, because sandstone, it will create and dissolve this damage. However, in carbonate, we are generating something called wormhole. And the wormhole will allow us to bypass the damage, create a really infinite conductivity, small channels that can bypass the damage and give us a really high permeability near the wellbore area. The third category, which is can happening in both, if you have a damage and the damage is a little bit deeper inside the formation. So if you will be able to use a high rate, in this case, matrix acidizing can be still a good option to use. But if you cannot do a high rate, in this case, you can also think about fracture treatment. So this is a case that is, you are talking about both can be done or can be selected depending on the injection rate that you will allow on the surface. And also don't forget about economics. Matrix acidizing is cheap treatment. However, hydraulic frac is very expensive. So you need to look how much production I'm expecting from this well. And it's economically, if I'm improving the production, I'm getting my money back from hydraulic frac or not, because of the expense of the treatment. But if you can get a similar or close result by matrix acidizing, usually that will be the easiest and the cheapest way to go. So before moving to the next section, does anyone have any question here? Okay, I cannot see any question there, so let me move to the next part, which is acid type. For acidizing, we have a different acid that we typically use for matrix acidizing. Let me start with the first one, is the organic scale, organic acids. And typically we have two main acid system. Hydrochloric acid, which is HCl, and that's a main acid for matrix acidizing, is the one that most used acid. And we will discuss each one of them in the upcoming slide. The second one is hydrofluoric acid, which is that's a main acid for sandstone formation. So when you have a sandstone treatment, you must have some sort of HF treatment from HF acid. It can be applied as directly HF, or you have some sort of a chemical that will be converted downhole to HF treatment to be able to dissolve, because that's the only acid system that can be able to dissolve silica and the clay mineral. So therefore, for sandstone acidizing, HF acid is the main acid that we are using. Also, we have something we call it organic acid, and we have mainly three chemical: acetic acid, formic acid, citric acid. Is a little bit expensive than HCl, but it's a much less corrosive. So you typically use them when we are having a high temperature scenarios. The third type is blend, and as engineers, we like blend. So by blending two acid system, usually we're trying to get or maximize the benefits from each system by itself. So HL, HF system. So in this case, we have system that can allow us for sandstone acidizing and minimize the precipitation that can be happened because of the HCl in the formulation. Acetic formic, so we know that which can be organic in blend, and again, acidic each one of them is a good acid system, but the solubility is not much higher. So when I'm combining two acid system, I'm getting a much good solubility here. Forming HCl, so I'm getting both, like the benefit of both, the benefit of reducing the corrosion rate a little bit, and also getting a good solubility from HCl. So as engineers, we like to blend different acids because we are getting a benefit of each acid itself. And we have some sort like specialty acids, and the use of specialty acids is very neat. Like I would say, only like maybe 5% of the jobs typically done by some sort of a specialty acid. Usually it happens when the temperature is too high, or you have some really sensitive formation that the previous acid system cannot work. Example of it, aminocarboxylic acid, GLD, MSA, all these acids is not typical acid that we're using in our daily acid jobs. But it's like a special, if you have a certain condition from temperature, from clay sensitivity or formation sensitivity, or uh, reservoir fluid sensitivity, in this case, that's when we are using this special acid. But I would say 95 of our typical acid job is done by HCl, HF, or some sort of acidic formic citric type of blend. So we can go each one and we can go through one, like really one by one. So HCl has a lot of advantage. Is the most used acid in acidizing world. The good part about HCl, it has a really wide concentration you can use. You can use it between 3% up to 28%. And the more acid concentration you have, the higher dissolving power that you have. It can dissolve much higher and a more capability to dissolve the rock. As an example, like 15% HCl can dissolve 1.86 pound of calcium carbonate. I'm talking about 1 gallon here of the material. So imagine if you have a gallon of HCl, 15%, you are dissolving almost 1.86. That's a lot of material that you dissolve downhole. 1.86 pound of calcium carbonate downhole. That's a really big amount. And if you are going 28, it will be multiplied by 2. It will be like almost 3.4 pound of calcium carbonate. So it has a good capability to dissolve a huge amount of formation. The third benefit, the cost. Really cheap chemical. We're talking about like almost $1 per gallon type of cost of fluid. So you can actually pump a lot with a very cheap treatment part. And the most thing that we like about the HCl is the reaction product. It's completely, majority of them is completely water soluble. So for example, the action rate, like if HCl react with a calcium carbonate, it usually produces calcium chloride, CO2, and H2O. And you can see the calcium chloride will be completely soluble in water. Until all the acid concentration from 3 to 28%, all the produced calcium chloride will be completely soluble in water. So don't have anything to precipitate downhole. Everything will be cleaned. So when you are using HCl and carbonate, you are merely having enhancement in porosity and permeability because of the solubility, because there is no precipitate happened. Similar for the dolomite, which is calcium magnesium carbonate. In this case, you have the calcium chloride, magnesium chloride, and both of them having good solubility in the water, so everything will be completely soluble. And CO2 is gas, and H2O just water. So you don't have any concern, any negative effect from the reaction product. Everything is solubilized. However, the concern about HCl is the corrosion. So HCl is a very strong acid system. It can actually corrode your pipe. So if you are bumping through the casing or through a pipe or through coil tubing, you need to be sure that you have a corrosion inhibitor. Some additives will go with it that will allow it to protect the tubing, because you don't want to corrode your pipe. It has a high corrosion rate, so we must use with it corrosion inhibitor to reduce the corrosion rate to the acceptable level. Second one, the reactivity. As soon as HCl see carbonate, it reacts almost instantaneously. Very fast reaction. Therefore, we need to be sure that we have enough concentration, and we have a challenge when we are talking about HCl, if how we can deeply place it inside the formation, because the reaction rate is very aggressively. So we need to bump it with sometimes higher injection rate, or with using some sort of a retarded systems to allow it to go deeper inside the formation and be effective at deep condition, because we don't want to consume all the acid in near wellbore area. Third concern we have is rock and reservoir flow compatibility. So HCl is a pretty good acid system. However, it has some issue if you have some asphaltene in your oil. So usually it gives you sludge, gives you asphaltene precipitation because of the low pH part. And if you have a light clay, a lot of time HCl can break this clay and cause some fine generation. And if you have iron hydroxide, it will definitely have iron precipitation inside the formation. So really you need to be sure that before the selection of HCl, you have to be sure that is all the rock that you have downhole, all the oil that you're having can be compatible with HCl. And if it's not compatible with HCl, that is the fourth one. So we need to add some additives to make it compatible with HCl. So for sludge, we need to put anti-sludge agent. For clay, we need to put a clay inhibitor. For iron, we need to put iron control agent. So we need to put a lot of additive there to be sure the compatibility between the HCl and the formation if we're having anything. That sometimes make the treatment a little bit expensive because of the additives that we have, not because of the acid itself, but because of the additives package that we have. And the additives package is actually one of the main difference between different service companies. So if we have, like example, the three big ones, Schlumberger, Halliburton, and Baker, actually the three are good. And the three were using the same HCl. So there is no difference between the three providing HCl. HCl is just the main chemical. However, the main difference between these three companies will be the additives that they will provide. What will be the best corrosion inhibitor that they are using? What's the iron control agent they are using? And how effective, how compatible with your formation? So that's mainly the way that you are selecting between surface company provider is based on the additives that you provided to you. So any question here? Excellent, no question. So let me move to the next slide. So the second acid is the HF acid system. And again, that is when you hear HF, that's what we're mainly talking about sandstone acidizing. We are not using HF for any carbonate acidizing. HF, when react with calcium carbonate, it produces a calcium fluoride, and this is a precipitate material. It will be damage the formation. Therefore, we are bumping only HF in sandstone acidizing. And the good part about HF is HCl will dissolve carbonate, will dissolve this scale, but will not be able to dissolve the silica or clay. HF will be able to actually do that. So HF is the only acid system that can be able to dissolve the silicate, the sand, and the clay. That's why are mainly being used in sandstone formation. The good part were actually can be inhibited up to 350 Fahrenheit, so can be used really at higher temperature without any issue. And when we are bumping HF as a system, we typically bump it in combination of HCl. We do not bump it alone, and I will talk about this one in the next slide. But just to highlight, like if you have 1 gallon of HCl HF system, it will only dissolve 0.217 pound of sand. Remember, 15% HCl 1 gallon in carbonate, it dissolves 1.8 pound. Corresponding to our HF system, we're talking about 0.217. So you can see the difference between the solubility power of HCl in carbonate, which is really huge, versus HF in sandstone, which is a little bit lower, but still good enough to enhance and give us a better permeability after treatment. So the reaction rate of HF is a little bit not favorable like HCl. We don't like mixing HF with a calcium carbonate. We have the pen. So when you have HF, we have calcium carbonate. You can have also calcium bifluoride, sorry, and this will precipitate immediately. This is something is not soluble in water. So therefore, before we are injecting the HF, we usually like to inject a pre-flush of HCl. And the idea of having a pre-flush of HCl is to dissolve this calcium carbonate before we are injecting HF. So we are not seeing this precipitate. The second part, when the hydrofluoric acid reacts with the sand, it actually produces another acid called flocyllic acid, which is H2SiF6. And this acid actually can react with the sodium and potassium from the clay. It will be able to dissolve it, and that's how it dissolves the clay minerals. But the reaction product is actually, again, is not soluble in water. It's insoluble. However, the good part about it, it does not precipitate until the pH become like 2 or higher. And that's why we are always the time when we're talking about sandstone acidizing, we are combining both HCl and HF together. The reason that we're adding HCl to the HF is to keep the pH of the solution is less than 0 or around 0, so less than 2. If it is less than 2, these two products will be still in solution and will not be precipitate, at least near wellbore area. Then you are actually pushing all this material deeper inside the formation. The pH will be at deeper inside the formation, will be mixed with the formation water, and the pH will be increased, and it will precipitate really deeper inside the formation, keeping the near wellbore area pretty clean, and all the damage in the near wellbore area will be dissolving. So what's happening there? You are removing the damage from the near wellbore area, which is the key area for you for the skin, and having a precipitation, but this precipitation will be happening really away from the wellbore, when the effect there will be much less. And that's simply the way how the HF acid doing it. So after the HF, let's talk about organic acids, which mainly we have the three acids that we're talking about: formic acid, acetic acid, and citric acid. And the advantage of using organic acid against HCl, for example, is two things: low corrosion rate. It will not affect the pipes. So you can bump it with a minimum effect on the pipe. So if you are having a chrome 13 pipe, or you're having some pipes that you are using and you really protect it, because replacing this pipe is super expensive, especially if you are talking about offshore environment. So it's not easy to replace your casing or your piping, the production pipe. In this case, maybe you force to use organic acid, or sometimes use lower HCl concentration to be able to inhibit it. Second, the reaction at higher temperature. You can inhibit it for high temperature, so you can easily use it up to 350 Fahrenheit without any issue. And again, because of this advantage, we'll be able to use it if we're having a long contact time. So if we're bumping a job for 8 hours or 10 hours, HCl will be really corrosive. So moving to the organic acid will allow us to be able to bump the acid without concern of the corrosion. If you have a really a high expensive, or what we call it, a low corrosion steel that you are actually putting there with some sort of external layer to minimize the corrosion that's happening because of the produced water, because of the water during the injection or during production, or due to if you have H2S environment or CO2 environment that during the production phase, you are using a really expensive type of tubing system to minimize the corrosion that happened during the production. In this case, you don't want this tube to be dissolved significantly in the acid during your acid treatment. So in this case, for these cases, if the HCl is too corrosive for it, we are using organic acid, either acetic, formic, or citric acid for that. Third, if you have iron in your formation and you need an acid that's compatible with iron, in this case, that's organic acid will be another usage for it. Because actually, a lot of these acids can work as an iron control agent. When keep the iron in solution all the time, and does not precipitate inside the formation. So moving to the next slide, talk about formic acid. As chemistry, it is called HCOOH from the composition point of view. Again, simply can be used up to 300 Fahrenheit without any issue. It is completely immiscible in the water, so if everything will be solubilized in the water, life condition, and also the reaction product for it will be completely miscible in the water. It is actually, this acid, formic acid, is stronger than acetic, but weaker than HCl. So from strength point of view, HCl will be the most stronger one, then formic, the second one, and the acetic will be the last one. And the reaction rate is fast, but is much slower compared to the HCl. Typically, we are using it between 8 to 10%, but the most common concentration for formic acid is 9%, which has an equivalent dissolving power to 7% HCl. So if you have 7% HCl, it will be dissolved same amount of 9% formic acid. But that can also give you a good indication about the strength of the acid. A second one, acetic acid, which is the from corrosion point of view and from strength point of view, is the lowest one compared to formic and acetic, formic and HCl. It can be inhibited up to 300 Fahrenheit, 350 Fahrenheit formation without any issue. That's a very high temperature to use it. And again, you can use it also in 10% concentration part. So usually like 9-10%, that's a typical recommendation for acetic acid. We don't usually go a higher amount than 10%, because if you start getting higher amount than 10% acetic acid, you may start seeing the calcium acetate, which coming from the reaction product, start to be insoluble in the water. So that's why we are limiting ourselves here to 10%. The good part about acetic acid, it reacts with the clay very nicely. It does not cause any swelling, does not cause any fines. So if you have a really sensitive formation and you like to do an acid treatment that will remove the carbonate without affecting the clay, in this case, acetic acid usually is a good recommendation to be applied. So that is about the acid type. I'm not sure if anyone has any questions or keep moving. So let me look to the chat pretty quickly. So no question here. So if anyone has any question, please feel free to type it. I prefer to cover it one by one during each section than waiting at the end.
There are some questions in the Q&A.
I cannot see them in this case.
So Mayar, if you see the Q&A section, can you read the questions for Dr. Ahmed? I can read them. So the first question, how do we know there is no damage in the well?
From reservoir engineering and production and well testing models. So first, each well will have some sort of a reservoir model associated with it, and you calibrate this model, and you have something called type curve analysis when you are expecting reduction in the production with time. Second part, you do well testing, pressure build up or drawdown test, and from these two items, you can actually define or calculate the skin factor. If you find you have a zero skin factor, you are good. There is no damage. But if you find you have a positive skin factor, in this case, that's a good indication of you have damage. And as soon as you have damage, you start looking back what will be the expected type of damage you are having based on the new well, old well, or injection well type of scenario, and looking for each one, try to identify what sorts of damage we have.
The second question, I understand that you need to know, you need to increase the KH, but why would you want to increase the porosity? It seems like misunderstanding.
So acid, when it dissolves the rock, it will affect because you are dissolving the rock, so you are creating void. As soon as you're creating void, you will have the porosity, local porosity, not overall porosity of the formation. It's the local porosity of the area that's been treated. So as soon as the porosity of this area will be increased, relatively for it, the permeability will go increased. And we are talking about a local area, not reservoir scale. We're talking about local area when the acid reacts. That's how it's happening, because you are dissolving and you are creating void or vugs. As soon as that will reflect in the porosity increase, and as soon as reflect in the porosity increase, that will improve the permeability of the formation.
The last question, what is the mean of acetic acid 10% normal?
So acetic acid is a chemical that has this formulation CH3 COOH. And when we are talking about normal concentration, that is the typical concentration that we are using is 10%. So this acid can be delivered in the field as a concentration 90%. So this means like 90% as standard concentration coming, 90% acetic, and 10% mixed with water. That's what percent. Then you are diluting it to 10% by dilution, 10% acetic acid, and 90% the remaining will be just water, and mixing them and pumping them inside the formation.
These are all the questions we have right now, so please go ahead.
Okay, excellent. Let's move to the acid additive section. And again, like all the acids that we're using, HCl, HF, organic, acetic, formic acid blend, all of these standard commodity product. You can buy it from whatever service company. There is no change about them. HCl is HCl, HF is HF system. The main differences will be the added additives, the component that you added to the acid to make it, how can I say it, to make it better performing. So we have a bunch of acid additives we have. The most important one, the first one will be the corrosion inhibitor. And no acid formulation will be pumped without corrosion inhibitor. You cannot, even if it's a small amount, even really saying that we're not thinking there is a corrosion, low temperature, nothing, we always should have a corrosion inhibitor. We need to protect the tubing. So corrosion inhibitor is a must additives. You have it all the time. You have something called corrosion inhibitor intensifier, that is like some sort of additives that you add it as additional to the corrosion inhibitor when the temperature is higher than 200 or 250 Fahrenheit. In this case, we're adding the corrosion inhibitor intensifier. Iron control agent, usually again one of the popular system, especially if you are expecting to have a higher corrosion rate. So if you have a higher corrosion rate, corrosion means you are corroding the pipe, and the pipe is steel, iron. So you need to have some sort of chemical that will keep this iron in solution and does not precipitate. Anti-sludge agent, if you have asphaltene usually will do sludge. Sludge will be like a very viscous, heavy material that will stain the oil and will block your permeability. Solvent, that is when you're having some sort of organic deposit, like some sort of xylene, toluene type of treatment that can dissolve the organic. And retardant, that's chemical that we are adding it to lower the reaction rate of the acid. And that will give us a really deeper penetration of the acid. So it can go deeper and have a deeper effect, have a good deeper effect of the acid inside the formation. That's the retardant acid. So we'll cover a few of them. Like the first one and the important one is the corrosion inhibitor. And again, it is always necessary. There is no acid formulation without corrosion inhibitor. If you feel it, that's when there's something wrong. So it's something always to be happening there. Sometimes we add with a corrosion inhibitor something called the corrosion inhibitor intensifier, and that's usually when the temperature is too high, like above 250 Fahrenheit. If the temperature is high, that's when we use the intensifier. If the temperature is low, we don't use the intensifier. Corrosion inhibitor is a very nasty material. It's a mixture of a lot of surfactant there and can damaging the oil well. It can make the oil wet. And if you are make the formation oil wet, it can actually reduce the effective oil permeability. Therefore, when we are applying the corrosion inhibitor, we usually like to apply the minimum corrosion inhibitor that will give us the acceptable corrosion rate from this one. So we do not want to bump more of the corrosion inhibitor because it has a negative effect on the reservoir. But we need to bump the minimum amount that will give us a good corrosion rate. The dosage, usually it's between 1 to 10 GPT, which is 0.1 to 1 volume percent. That's a typical usage that you're having. Depending on the temperature, depending on the steel, depending on the acid and acid concentration, that is how the concentration can go from 0.1 volume percent up to 1 volume percent. Sometimes we can go higher than 1 volume percent in case if we're having really high corrosion rate or really high temperature. That's in the cases that we are going more than 1%. But if you are seeing that case, you need to ask your surface company to provide a detailed corrosion rate study to confirm these numbers. Don't really bump a huge amount of corrosion inhibitor because it may have a negative effect on your formation. And corrosion inhibitor is not one fit all. It's not one additive fit all. So you have a corrosion inhibitor for each acid system. So for each real acid system, you may have a certain type of corrosion inhibitor. For formic or organic acid like formic acetic, you will have a completely different one. So it's not only one chemical from surface company to fit everything. So usually surface company have, like I would say, like 20, 30 different corrosion inhibitors. And each one of them will be depending on whatever acid we are using, whatever concentration you are bumping this acid with, and whatever metal you are trying to protect. So there is corrosion inhibitor for steel pipes, and there's corrosion inhibitor for chrome 13 pipes. So depending on the type of the corrosion, depending on the type of the material and the acid, you select the corrosion rate. Also, temperature and contact time will have an effect, but usually the temperature and contact time affecting more the concentration. So the higher temperature, the higher contact time, usually you need to use more and more from the corrosion rate. The concentration will go up. So how you do the corrosion rate? You get something called coupon, metal coupon. So you get a part of the tube and you're cutting with a certain dimension, 1 inch by 1 inch, and you get this coupon and put it inside your acid and put it at the same temperature and at the same time that you are bumping inside the acid. So if you are bumping acid for 6 hours and the reservoir temperature is 200 Fahrenheit, so you get a metal from same tube that you are bumping through it, put it inside the vessel, put it under the same pressure and temperature at downhole, 200 Fahrenheit, 5,000 psi, 5,000 psi, leave it for 6 hours, and after 6 hours, you release it, you take the coupon and weight the coupon after. You have the initial weight, you have the final weight, and between them, the acid will be corroding, so you will lose some metal. And convert these losses, the weight losses, into some sort of corrosion rate, which will be pound per feet square. So you know the coupon dimension, 1 inch by 1 inch. So you have the surface area, you know how much gram you are using, and then you have like the mass over area converted to pound per square feet. And we have a 3 type of corrosion rate, and that is like a standard we all of us follow it up. For carbonate non-chrome tubes, you need to be less than 0.005 pound per square feet. If it's cold tubing or chrome steel tube, we're talking about 0.02 pound per square feet. And this is, I will not say standard, but that's the best practice that our industry like to have. These 2 numbers is really critical. You don't want to exceed any of these numbers in the corrosion rate testing. Usually, as a completion engineer or the production engineer working the operator, you ask your surface company to provide this testing for you, and you check these 2 numbers. If you are having a carbon steel tube, you would like to be less than 0.05 pound per square feet. If you are injecting your acid through cold tubing, or the downhole production tubing is a chrome steel, you need to be sure that you are less than 0.02. And you do the testing based on the reservoir temperature, and you do the testing based on the timing, the contact time that you have. So you have the corrosion rate, and you have something called pitting scale. Betting scale is something like you can see it here. Like you see this bug or this hole or this punch inside the steel. That's something we call it betting. And we have a scale going from 0 to 5. That's like standard betting scale. And depending on how severe it is, you are going 0 when you have no